Well, this is our fifth presentation of 12 on the structure and properties of organic molecules. It's our second one on resonance, and resonance is worthy of two presentations. It's very important to understand resonance theory and how to use it to look at not only cations, anions, but also neutral molecules like this of a certain type of penicillin where R is not defined. And we did three things in the last presentation on resonance. We looked at the theory of resonance theory, and we did it by connecting it to orbital-based theory, which is somewhat unique because resonance really preceded orbital theory of bonding. But we can tie those two together. So we did that. That was the first thing, covering theory. For an example, we looked at how we can see before we draw any lines showing resonance delocalization of this negative charge, we made sure to see the orbitals that line up, the p orbitals specifically, that line up that allow for resonance delocalization of pi and lone pair electrons. So we looked at that. We looked at the resonance theory through, I guess, p orbitals. And then second, we looked at the rules for drawing resonance forms. We looked at this sheet that presents how we can approach positive charges, negative charges, and this second presentation will focus in on neutral molecules using this sheet to, I guess, show how we could draw neutral molecules or to know how to start drawing resonance forms for neutral molecules. That's our sort of gained. This was the second thing we sort of discussed, and then we applied that to an anion. Well, that was our first presentation on resonance. The second one here, I'd like to focus our presentation on neutral structures because that's what we see a lot of in the textbooks that have something describing organic chemistry. We'll have a lot more neutral structures. Why? Why more neutral structures than cations and anions? This is being an anion, and we can have more discussion of neutral structures because they're just more prevalent. Anions and cations are higher energy. So it just makes sense that we'll see in a representation of organic chemistry more discussion of neutral molecules. That's what we start with, and that's what we usually end with. And maybe less discussion or less focus on, I shouldn't say less focus, but we'll see intermediates that are cationic and anionic. So sometimes it's helpful to understand resonance for the high energy structures, but it's also helpful to understand resonance for the low energy structures, where they start and most often where they end. So what do we want to do with this recording, the second one on resonance, is we want to review a little bit of the rules for drawing resonance forms for cations and anions. Then we'll move into discussion of resonance for neutral structures, and then we'll do one application with a neutral structure. So let's review a little bit for cations and anions. Now we said for cations and anions, if you refer back to that page that has the instructions or the rules for drawing resonance forms, you'll see that it says move to positive charges. Move to positive charges. So in the last presentation, that page that discussed how to start drawing resonance forms for cations, anions, and neutrals, the rules for cations and anions were a little simple. Just start at the charge. So here we have a positive charge on this particular cation. Now it's important to not forget that we can see the orbitals underneath the letters and lines now. So we see an empty p orbital here coming straight out towards us. And we can come at that empty p orbital with nearby pi and lone pair electrons. So we can come from the left. I'm going to just talk about how we move. I don't want to draw my resonance arrows because I have a lot of directions I can come from. But I'm just going to describe it. Lone pair to pi, we can take one of the lone pairs, put it in a p orbital by making this sp2 hybridized. The oxygen being sp2 hybridized would have one lone pair in a p orbital and one in a hybrid orbital. So we can see that we could establish a p orbital overlap. We saw that was important in the last presentation. And we can have that come down to satisfy the empty p orbital, and the positive charge, by extension, would move to the oxygen. So that would be our first resonance form we could consider. We do see a delocalization or a spreading out of the positive charge. Just like in the last presentation, we saw a spreading out of a negative charge. So we can also come at it from two other directions, though. We can come from the top left, swinging the pi electrons over. Now again, don't lose the orbital picture. Empty p orbital, two p orbitals that are bonded together through a pi bond. We do have a lone pair here, but we cannot get this lone pair involved. Why not? Because if you look at the hybridization, we know it's sp2. We are using the 1p orbital to make this pi bond. So just to do some accounting, we can say, hey, this changed from sp3, well, no longer sp3, it's in a pi bond. This nitrogen is sp2 hybridized. It's sp2, and we use that as a door into the structure. sp2 hybridization, we know that we have this electronic configuration. We know that p orbital is used to make the pi bond. We have two sigma bonds, so there go two hybrid orbitals. This lone pair has to sit in a hybrid orbital. Again, using the hybridization to see where everything is in the molecule. So these electrons will not be used in resonance delocalization. Why not? They're hybrid. They're in a hybrid orbital, so we cannot use them. They need to be in a p orbital. So let's leave them alone. We can swing the gate here. We can move these pi electrons over. But if we do that, we leave nitrogen with only 6. You can never leave nitrogen or oxygen with only 6 valence electrons. I'm just not happy with that. So we can move these electrons over, but at the same time, move these over. So 2 arrows you could draw for that. And we would have, if you draw those 2 arrows, we'd have a pi bond here, because we moved that up, and at the same time we moved this over. And now we have a new structure, and where is our positive charge? It would have moved here, because this is left in the cold. The pi bond left from this carbon. So that's the positively charged carbon, a new place that we can spread out the positive charge. A new place that can take the positive charge. Alright, we're on our last one. As far as the initial 3 that we can draw looking at this positive charge, we came at it from the top right, top left. We can also come at it from the bottom left. There's a bond here. We can swing the pi electrons over, and we can get, I'm just not drawing the lone pairs on the nitrogen here. They're there, but we're just, for sake of time, just drawing. And these are the rules for skeletal structures, just to draw the N's and O's, but not their lone pairs. So the positive charge, if we come from the bottom left, would be here. So we look at these 3, and yes, they all have the positive charge at a new position, and I was able to reach them in a valid way by doing what is allowed for drawing resonance forms. They are valid resonance forms. They're different from this one. So right now we have 4 resonance forms. These are all, again, mixed into the actual structure. And any one of these 3 can represent that actual, any one of these 4, sorry, 1, 2, 3, 4, can represent the actual structure. But we're not done yet. We want to make sure we can't draw any other resonance form wherein the positive charge is moved to a different position. Well, this one, the only thing we could do is move back to the positive charge these pi electrons. So you can usually just take what you have as new and work from there. This one can't go anywhere. It's done. The only way I can go is back to what I already have. But here, remember we started kind of swinging electrons in a clockwise manner. We could swing this down, put the positive charge here, and we know that no other resonance form has the positive charge at this position at a carbon at the top between the nitrogen and the initial carbon that was positively charged. So we can say, hey, that's a new resonance form, a valid resonance form, because all I did is swing the pi electrons down, and I'm going to go ahead and show it here. We can swing the positive, oops, that's not a very good drawing, but I think we can still salvage it. So the positive charge swings to this position, the pi electrons swing down, and this is our new resonance form. I'm going to go ahead and make a little bit more fuss about this one, because we can actually reach it using this one as our starting point also. So it doesn't matter. You can try to find out, you can try to figure out on your own how you can get from here to here. I think you can see that fairly quickly. But this is it. These are the 4 additional resonance forms to the initial one that we can draw for this particular pyrrole ring that's positively charged. So again, how do you know when to stop? You just keep drawing resonance forms till you notice you're just repeating yourself, and that's how you know to stop. So how do we know which one of these is most contributing to the hybrid? We have to consider, if you go back to that page on our recording discussing resonance forms and how you consider their contributions, it was satisfaction of octet rule, minimization of charge, and stabilization of charge. So we know that all of them have a positive charge. But that was the second consideration, minimization of charge. The number one consideration was octet rule. If you look at these three here, 1, 2, 3, and even this one here, the carbon has only 6 electrons around it. Because off of this carbon we have 3 bonds. Off of this one you say, well, there's only 2 bonds. No, there are 3. There's a hydrogen here that's not shown. So each of these, A, C, D, and E, have carbons with only 6 electrons. But B, the positive charge is on an oxygen. But this oxygen had 2 lone pairs, so it still has 1 lone pair left. So it's still satisfying the octet rule, even though it's an oxygen with positive, and you'd say that would be least desirable. That's the third consideration, location of charge. The first consideration, most important, was octet rule. This one satisfies the octet rule. 2, 4, 6, 8 electrons around it. B is most contributing. Well, that was a long review of cations and anions, but let's get to our second task of looking at neutral structures. How do we draw resonance forms for neutral structures? Well, first of all, it might be helpful just to put 2 structures against each other where one has resonance and the other one doesn't, and look at why they don't. Well, we know hybridization for these 2 carbons is sp3. And we know then that if a lone pair was on this nitrogen, and it is, we know it by drawing skeletal structures, unless it was charge was shown that lone pair is present. There's no place for the lone pair to delocalize. There's no p orbital on this carbon for this to go. So there's no chance for resonance delocalization. There's just nowhere for the lone pair to go. There's no neighboring p orbital. So the ball and spoke model, kind of this was created using computer modeling, reflects this sp3 hybridization. The nitrogen has bond angles between the H and this carbon that's near 109. So we can say the hybridization above is indeed sp3. But when we look at acetaminophen and model that, this nitrogen does not reflect sp3 hybridization like this one. Well, why not? Well, first of all, it'd just be good to notice that we do have neighboring p orbitals. Here we have a p orbital and overlapping with a p orbital on this oxygen. We have the benzene ring neighboring this lone pair, which also has a lot of p orbitals or pi bonding network that we could delocalize into. So there's going to be a strong desire, mostly because of what we see on the right here, but also because of the benzene ring, for this nitrogen to be sp2 hybridized with the lone pair being in a p orbital. That's reflected here. The angle 116 between the hydrogen and this carbon bond, nitrogen-carbon bond, is 116. That reflects something more of sp2 hybridization than sp3. So let's look at this acetaminophen in more detail. When we look down the line between the methyl group and this OH, it seems that everything is in the same plane. That also reflects that the atoms starting from here are all sp2 hybridized. Of course, the methyl group, these 2 hydrogens, two of them have to be above and below the plane. One can be in the plane, but the other, because this is sp3, has to be outside of the plane. The other sp3, other 2. But from here on, it seems fairly planar. That would suggest that all of the atoms are sp2. And the rules that we can remember for heteroatoms that are not in a pi bond but are next to a pi bond is that by resonance these become sp2. Resonance drives them to be sp2. So lone pair on an atom next to a pi bond, those atoms tend to be, not always, but tend to be sp2 hybridized. Now if we look at the electrostatic potential map, we also notice that not only is this planar all the way from this carbon out, but we notice that the nitrogen which is here. This is the methyl group. This is the oxygen. This nitrogen is electrostatically partially positive. That blows students' minds. They usually think N's and O's are partially negative. But the electrostatic potential map, this is a sort of a measure of where electron density is. Red reflects excess electron density, blue reflects low electron density or lack of electron density. So we have a nitrogen that's shown in blue indicating that it's deficient in electron density. It's low in electron density. Can we draw a resonance form that explains that this is sp2, the planarity of the whole of the acetaminophen minus the methyl group, and the partial positive charge seen for this nitrogen? I think we can. And let's finish with this example and be done with our second video on resonance. So neutral structures, again, where we are often focusing our eye on organic chemistry. A lot of neutral structures out there. Let's see if we can draw a resonance form for acetaminophen. Now, one thing to remember for any neutral structure is you want to focus on the spice. The nitrogens and oxygens provide spice, partial charges, things where reactivity is going to be. So let's go ahead and tag our hybridizations. We know this is sp2 hybridized. We know the ring has sp2 hybridized carbons. This is sp3 because it has 4 single bonds off of it. But these nitrogens and the oxygen here, we said, are indeed sp2 hybridized. So just kind of reviewing some things on hybridization. And why this is important is because it'll allow us to kind of circle where we have p orbitals that could overlap. This was sp2, sp2, this is sp2, sp2, sp2. So we could say, hey, what's going on with acetaminophen is that we have a planarity because all the p orbitals can be overlapping and setting these atoms in a plane. So we're looking down the p orbitals in a sense. All these atoms have a p orbital coming straight out at us. And I'm circling that zone that we have to consider for resonance, potential resonance, and where we go. So let's start with the the nitrogen and start drawing resonance forms that involve the nitrogen. Now we could do that for oxygen here, but for sake of time, I'm going to just focus on the nitrogen. And that's what you typically do with neutral structures, is you just try to see what the influence of every heteroatom is on the molecule. So we're going to start here. Why? Because nitrogen has higher energy to its electrons. It's not as electronegative as oxygen, so it has less hold on its electrons, and they're flowing around or have relocated in the structure to a greater degree. So let's start there. So let's go ahead and move to the carbons. So we're going to move electron density from the nitrogen to the carbons. You say, well, how do you get started? Well, with the nitrogen that's not in a pi bond, but is next to a pi bond, you push towards the pi bond. So lone pair to pi, I'm not going to draw it. I'm going to draw it for the move to the carbonyl, but for now I'm just going to leave this clear for discussion of this interaction. So nitrogen can take its lone pair to a pi bond, pi to lone pair. So we could have our first resonance form involving the nitrogen pushing into the ring. You say, well, is that needing to be considered? Yeah, because it's happening. Maybe not to the same degree as other resonance forms are being expressed, but we still have a push to the carbon. Now, the only thing I did was lone pair to pi, pi to lone pair. And you often see that move with neutral structures. Lone pair to pi, pi to lone pair. We're leaving everything else the same. Now, the nitrogen would be positive. The carbon here would be negative. And, of course, we could continue to push this negative to other carbons within the ring. Lone pair to pi, pi to lone pair. Lone pair to pi, pi to lone pair. So these two could also express that negative charge. So this is moving towards the benzene ring. Now we can also consider, as we look at drawing resonance forms, we can look at the pull effect of oxygens in a pi bond. That might be a place to start. If you don't have a lone pair next to a pi bond, you can just consider atoms or heteroatoms that are in a pi bond. So here we have a O that's in a pi bond, we're going to consider this pi to lone pair, the polar. This is a polar. I should have tagged that at the beginning. This is a pusher. It's a heteroatom next to a pi bond, heteroatom next to a pi bond, and this also is a pusher. Heteroatom next to a pi bond. That should have been done at the beginning. I apologize. You can tag your O's and N's within a neutral molecule as pushers, like we saw here. This one pushed to the benzene ring. We're not going to do it with this structure. We could have considered O pushing into this benzene ring. And the polar, we could also consider just starting with the polar, its effect, and let's do that. So we're not considering anything else except the polar and his effect on the molecule. Now this is the least favorite of all the minors because we're going to have positive and negative charge. That's going to be why all the structures down here are minors compared to this neutral structure. But this is the least favored because we have the positive charge on a carbon that has only 6 electrons around it. Alright, now we're about ready to get to our last one. The nitrogen can satisfy that positive charge that's starting to develop here to its right. It's pretty significant by just dropping the lone pair down. So what we can do, and this is what you often want to do with neutral structures, is you want to tether the polar to the pusher. In other words, use them both together. So we had the pole effect. That was at least favorite of the minors, but let's just put the push and the pole together. So lone pair is going to come down while this pi bond is coming up, or pi electrons are coming up. So we have the effect of the push and the pull together to give us our most favored minor resonance form. Why are they all minor? Because they have positive and negative charge. They are with positive and negative charge. They're dipolar. This is a neutral structure. So, and one last thing. I did not consider benzene ring to be a starting point for discussion of resonance. We looked at O's and N's because they set partial charges. We could have just done pi to pi, pi to pi, pi to pi. But this is kind of like rearranging chairs on the Titanic. It's not really critical because it's non-polar. And yes, is this a valid resonance form? You bet. Does it help me know? Does it help me see where the partial charges are? No. So I can draw again pi to pi, pi to pi, pi to pi. But that just doesn't really provide me with a picture of the partial charges. These minors do. All right, I think I'm going to need to finish. We'll start with the summary of our first 3 tasks that we've covered in the 5 videos or 5 presentations on structure and properties of organic molecules. We'll start our next one on just a summary of the first 3 tasks, which were drawing structures, designating hybridization, and now drawing resonance forms. We'll summarize that as we start our 6th of 12 presentations.